Okay, so this is a close-up of one of these quintessential sequences in the Blue Lias, where we get shales and limestones. And if we look at the cliffs behind us, that's really well demonstrated. We can see these regular cycles of limestone, shale, limestone, shale, limestone, shale. And those are part of what make the Blue Lias really famous, a really classic geological sequence. What you'll also notice, if we look just at this section to the side of me here, is that these major alternations, these limestone shales, these aren't the only patterns that we have in the rocks here. You'll notice that this layer of shale, for example, has a light grey, fairly soft rock at the bottom, this much more dark, much blacker layer in the middle, another one that's similar to the bottom, and then a limestone at the top. And these changes are fairly gradual. You can see in the bottom here again, and they represent different environmental conditions on the sea floor during the time of deposition. Now there are all sorts of chemical processes going on which are really complicated, but the basic essence of these rhythms is that the different colours and the different textures in the rock record represent degrees of bottom water oxygen conditions. So in the limestones here, and the limestone at the bottom here, we had well oxygenated bottom waters. So life could flourish on the sea floor. We had lots of worms, lots of trace fossils, the bivalves, and in the water column we had ammonites, ichthyosaurs, etc. And you'll notice that if we look at these limestones, they're really wavy, really hummocky, and that's an effect of all this bioturbation, which is the scientists' word for sediment mixing and for all your creepy crawlies burrowing and working away, but also it's full of fossils. So if we look here, we can see the cross sections of ammonites, pieces of shell in the surface, and that's why we know these conditions were really beneficial to life. As we move down the sequence, we can see that the amount of shells we get in each of these beds varies intensely. So in the sort of transitional zones, we'll expect some of the more opportunistic creatures, so oysters, the more hardy trace fossils, but generally there's less life and it's less diverse. When we get into these black rocks, these well laminated, organic rich sediments, similar to the shales that we're used to in places like Kimmeridge, for example, these were fairly devoid of life, and they represent oxygen poor conditions on the seafloor, where we get this fine hemipelagic fallout of clays and other sediments, and the only animals really living in this time were things that swam in the water column, so ammonites, ichthyosaurs, marine reptiles, and that's because they weren't dependent on oxygen conditions at the seafloor. And then, as we see just down the bottom here, we start to come back into these oxygenated conditions. And this rhythm, this separation, is one of the real sort of mysteries of the Blue Lias formation, and something that's attracted sedimentologists, geologists, paleontologists to the Jurassic Coast for centuries now, because understanding these rhythms gives us a way of understanding environmental conditions, how environments respond to things like global warming, CO2 levels in the ocean, and how that affects marine life. So it's a really useful representation of what we can expect some of our seas today to be looking like in hundreds of millions of years.